Hello grade 11s. In this video I want to talk about using the square identity when solving quadratic trig equations. Now just to give you a reminder on the square identity says that sine squared theta plus cos squared theta is equal to 1. But I can change it by saying if sine squared theta plus cos squared theta is equal to 1, then that means that sine squared theta is 1 minus cos squared theta. So if you look, sine squared theta is 1 minus cos squared theta. Or I can say that cos squared theta is 1 minus sine squared theta. So we generally use these two variations of the identity. We don't really use this one specifically. So how do we know that this is what we are supposed to do? Well, there are a couple of clues that we're going to be using the square identity, and those are the following. Number one, you have to have a square. So if you look at this problem, determine the general solution of 2 cos squared theta is equal to sine theta plus 1. Right there, it won't work if I don't have the square. So the other reason I know that I have to use the square identity is the following. I have these two different trig functions. I've got sine of an angle and I've got cosine of an angle. These angles are the same. That's the good news. If they're not the same, we are completely stuffed, then this problem doesn't work. But don't worry about that. With these particular problems, if I'm going to use the square identity, you will always have the same angle. So if you look at it, you realize I now have a quadratic trigonometric equation because of that square. That gives me a quadratic trig equation. But I have two different functions. And I cannot solve a quadratic equation with an x squared and a y, for instance, because that's pretty much what it would say. If I ignore the trigonometry and I just look at the algebra, we can say this is like saying it's 2x squared is equal to y plus 1, which would then require a simultaneous equation. Luckily, this is not an algebraic equation. This is a trig equation. And trig equations are wonderful because of the identities where I can change cos squared into sine squared. So that's what I'm going to do. Now again, brackets are incredibly important. I cannot state enough how important these brackets are, because we are going to be substituting a single term cos squared theta with a binomial, because cos squared theta is 1 minus sine squared theta. And if I don't put the bracket, I'm going to forget that 2 must be multiplied by everything. So I've got to distribute the 2. That's got to be 2 times 1, and it's got to be 2 times negative sine squared theta. Then, on that side, I've got sine theta plus 1. There we go. So now, I have to simplify, and when I simplify, I mean I have to put it in standard form for a quadratic equation. So remember, quadratic equations are normally in the form ax squared plus bx plus c is equal to 0. Now obviously we don't have an x there. We've got sine of theta that serves as our variable per se. But quadratic equations must always be equal to 0. And that's what I mean when I say standard form, get it equal to 0. So first things first, I'm going to distribute that 2, saying it's 2 minus 2 sine squared theta is then equal to sine theta plus 1. Now I want the 0. Now because this is negative, I'm just going to put the 0 on the left-hand side. So this is then going to be positive 2 sine squared theta plus sine theta. And then this is going to be 1 minus 2. So that's going to be minus 1. So this is now in standard form, like a quadratic equation. So it's like saying 2x squared plus x minus 1. So now what I need to do is I need to factorize it, because that's how we solve quadratic equations. We factorize. So this might be probably the most difficult part for you guys, because a lot of people struggle to do the algebra inside trigonometry, because they don't see this as one thing. They don't see this as sine theta being one thing, just like x. They see it as sine and as theta. Please, people, there's no such thing as sine. So sine theta is one thing. That's one variable. So when I factorize, I'm going to start by saying 2 sine squared theta is going to be 2 sine theta times the sine of theta. That's going to give me 2 sine squared theta. Then to get the 1, I'm going to say 1 times 1 gives me the 1. But I need to remember my outers and my inners needs to give me my middle term. So in this case, it's going to be plus there, so that I have plus 2 sine theta. And then I'm going to put a minus there, so that I have minus sine theta. And that then means that 2 sine theta minus 1 is 0. So that means sine theta is equal to 1 over 2. That's the first part. Or the second part is then that sine theta is equal to -1. Now, by the way, if you've looked at this and you go like, this is horrible, I really don't know how to do this, there is a way to make it slightly easier, and that is by using your silver calculator and using your equation function. But if you want to use your equation function, we obviously need to look right there, right there. So I'm going to go and I'm going to change it to mode 5, which is my equation mode, and I'm going to pick 3, which is my quadratic equation, which this is. So my A value is going to be the coefficient of that sine squared theta, so that's going to be 2. My B value is then going to be the coefficient of sine theta, which is 1, and my C value is going to be the constant term, which is -1. And if I press equal there, I get x is a half. But remember, we didn't solve for x, we solved for sine theta. So sine theta is a half. And if I press equal again, I get x is -2. But again, we didn't solve for x, we solved for sine theta. So that's why sine theta is -1. Now, the only annoying thing about this particularly is now I end up with 2 general solutions because I've got 2 ratios. So unfortunately, this does get a little bit long because I have to find a reference angle for this particular ratio of a half, and I have to find another reference angle for this particular ratio of -1. So I'm going to find the reference angle by putting the half into the inverse sine function. So shift inverse sine of a half gives me a reference angle of 30 degrees over here. And over there, I'm going to say shift sine -1 of -1 gives me a reference angle of -90 degrees over here. Okay. So now I just have to drop both of those reference angles into my general solution for sine. And please remember, sine has got 2 parts to the general solution. So the first part just says theta is equal to the reference angle as it is plus k times 360. And then somewhere on the page, remember k is an element of the integers, so you don't get penalized. The second part of that general solution for sine then says theta is equal to 180 minus the reference angle. So 180 degrees minus 30 plus k times 360. Then, simplifying that, we've got 150 degrees plus k times 360. So those are the 2 parts of the general solution for that particular ratio. But then I have to do the same thing over here. So there I again have to go and say theta is then equal to minus 90 degrees plus k times 360. And the second part of that general solution, theta is equal to 180 minus minus 90. So careful, minus minus 90 gives you plus 90, so that's going to be 270 plus k times 360. By the way, this is 100% correct, but you'll see sometimes what the textbook does is the textbook combines, especially if you have 0 there, or if you have 1 there, or if you have -1 over there. So these are the common ones. -1, 0, and 1 as your ratio. They like to combine these 2 into 1. Okay, and combining these 2 into 1 pretty much just means that you can just use your trig function like this. And you can ask yourself, and I can do it going this direction as well. You can ask yourself, where is the sine function equal to -1? So -1 is going to be over there. There it's -1, there it's -1. So if you look at it like that, you can say this is at minus 90, and then this one is at 270. Now, minus 90 and 270 is what's represented over there, plus then k times 360, which just continues, continues, continues. So actually, that is probably the easier way to do it. I know that I've now wasted a little bit of time discussing this, but this is probably the easier way to do it. I think the technique that I wanted to discuss with you works better if you have sine theta equal to 0. Okay, great. So that's that example. Let's try another one. Now, this one specifically is not the one I wanted to do first. Sorry, this one's the complicated one. Let's do this one first. So in this one again, we have that square identity, as you can see. We've got that sine squared theta right over there. Now, the reason sine squared theta is a problem is because this is not sine theta, this is cos theta. So there, and I'm going to put a bracket around it to remind you guys, we put a bracket when we do the substitution. So right over there, I'm now going to substitute the 1 minus cos squared theta in there. So I'm going to say 5 minus 4 times 1 minus cos squared theta plus 4 cos theta is equal to 0. Okay, let's pause. Right, so now that we've substituted that sine squared theta with 1 minus cos squared theta, we can then go and we can simplify and we can put it into that standard form of a quadratic equation, which means equal to 0. So there I'm going to have to distribute. That's why the brackets are so important again. So I'm going to say 5 minus 4 times 1, which is minus 4. And then minus 4 times minus cos squared theta is then plus 4 cos squared theta. Plus 4 cos theta is equal to 0. So that's going to be 4 cos squared theta plus 4 cos theta, and then that's going to be plus 1 equal to 0. So I'm going to factorize this one, again remembering my variable in this factorization is cos of theta. So I want to go and I want to get this one, so this is going to be 2 cos theta times 2 cos theta, which is going to give you that 4 cos squared theta. That's going to be 1 times 1, and this is going to be plus and plus because I've got the 2 cos theta plus 2 cos squared, cos theta is 4 cos theta. So these are identical, which means I don't actually have to now go and write 2 possibilities down. In this particular case, I can write down just the one possibility, which is that the cos of theta is equal to negative a half. And then from there on, I can do the general solution using negative a half and the inverse of the cosine function to find my reference angle. By the way, just a quick comment. A lot of the time, like with that previous example that I gave you guys, we have the situation that we have two possible situations that work, and because we have 2 possible situations that work, we can then go and we can work out 2 general solutions over here. But sometimes what happens is the following, just as an example, just to give you this one. If I had something like the cos of theta is equal to 3, and this would happen if I had a bracket that said cos of theta minus 3 is equal to 0. Now, the moment I have that, this one, people, you don't have to continue with that. That is not applicable. And the reason it is not applicable is simply because of the fact that cos of theta cannot be equal to 3. 3 is much too big to be a possibility for cos of theta. And the only way to see this is to quickly draw the cosine graph like that, and then hopefully you guys will remember the cosine graph goes from negative 1 over there to positive 1 over there. So it's impossible for the cos of theta to be equal to 3. So if you do get a situation where you have something like the cos of theta is equal to 3, you can ignore it. You don't have to do that one. Okay, so please just remember, and the same goes for the sine of theta. Sine of theta also doesn't work if it's greater than 1, or if it's less than negative 1, it doesn't work. So that's just to remind you if something like that should happen. By the way, if you forget about this, and you try and find a reference angle for this one, so if you go shift cos minus 1 of 3, you're going to end up with a math error. So whenever you end up with a math error, please remember, don't continue with it. Okay, so just don't continue with it. So that was, again, a bit of a tangent. I apologize for that tangent, but just in case you get a situation like that. So here we're going to find the reference angle by saying the inverse cos of negative a half. And that's going to give me 120 degrees as my reference angle. And then we're going to do the 2 parts of the cosine general solution, the first part being theta is just equal to that 120 degrees plus k times 360. Remembering somewhere on the page, please put k as an element of the integers, just so you don't get penalized for that. And then the second part is going to be using that reference angle, but negative the reference angle. So minus 120 degrees plus k times 360. So this particular problem is then done. Now, if you then go and you look at the next problem, this particular problem is pretty much as difficult as they get. And the reason this particular problem is as difficult as they get is the following. You'll spot you have cos squared theta over there. Now, cos squared theta is really not necessarily the issue. And the reason cos squared theta is not the issue is if you look at the previous examples, we said sine squared theta is an issue because we've got cos theta there. So we don't want two different trig functions, we want one trig function, and that's why we changed sine squared theta to cos squared theta. But in this particular problem, we say cos squared theta is not an issue because I have cos theta over there. So you're like, yay, let me keep it. And then you realize, uh-oh, I also have sine theta. So in this problem, because I have both sine theta and cos theta, which by the way I can't change. I can change this one, can't change that one. So because I have both of these, I need to go and I need to create a sine squared theta for this particular problem. And you go like, create a sine squared theta? Yes, you can actually create a sine squared theta. And it goes back all the way to the beginning where we might have forgotten about this part right there. And please remember, if we can read something in mathematics from left to right, I can read it from right to left. Meaning, I can take 1, and I call 1 the Easter egg. And because 1 is the Easter egg, I can expand 1 to sine squared theta plus cos squared theta. So right over here, here's my Easter egg, right there. This is my beautiful little Easter egg. I can take that 1 and I can change that 1 into sine squared theta plus cos squared theta. So please remember, this gets substituted with that. Then I write the race down, sine theta times cos theta minus 7 cos squared theta is equal to 0. Now you might look at that and say, well, this looks super complicated. How's this now solve my problem? It actually solved your problem perfectly because we can now put sine squared theta as the first term. Then we could put this combination term, so the plus sine theta times cos theta as my second term. And then because these two are like terms, I can say 1 of the cos squared thetas minus 7 of the cos squared thetas is minus 6 of the cos squared thetas. And I can actually factorize this. I can factorize this, just like I've been factorizing all of the other ones. It's slightly more complicated, but it's doable. Because sine theta times sine theta is going to be equal to sine squared theta. And that 6 cos squared theta can be 2 cos theta times 3 cos theta is then equal to the 6 cos squared theta. But I need to make sure that I can now go and I can combine these two to get to that middle term. So this must be plus, and this must be minus. So I've got the plus 3 sine theta cos theta minus the 2 sine theta cos theta, which gives me the plus 1 sine theta cos theta. So this factorization is pretty much the trickiest one that we've done so far. But once you've got that factorization, when you now write it down saying if sine theta minus 2 cos theta is equal to 0, then it means sine theta must be equal to 2 cos theta, so that's the first one. Or sine theta must be equal to negative 3 cos theta. Now these go back to the one where we use the tan identity. So it goes back to the one where I say, I'm going to go and I'm going to divide this one by cos of theta, and remember whatever I do on the left-hand side, I just have to do on the right-hand side. Which means sine theta over cos theta is tan theta, so tan theta is equal to 2, which actually gives me a very easy general solution to do. And I'm going to do exactly the same thing over there. I'm going to divide the left-hand side by cos theta, same thing on the right-hand side, which means sine theta over cos theta is tan theta, and in this case, tan theta is then equal to minus 3, because the cos theta divides into the cos theta. And now I can find the reference angles for both of these. By just using my inverse tan of positive 2. So my reference angle there is 63,4, rounded off to 1 decimal place. And over here, I will then just substitute the negative 3 in there. So there my reference angle is minus 71,6 degrees. And then I can substitute it into my general solution for tan, which is the angle 63,4 plus k times 180. And remember, the nice thing about the tan general solution, it only has one part. It doesn't have two parts. And I can do the same thing over there, saying theta is then equal to minus 71,6 degrees, my reference angle, plus k times 180. And please remember, somewhere on the page, just put k as an element of the integers. And that is then pretty much as difficult as these ones can potentially go. Right. Thank you very much for listening.